Today, we're going to have a little bit of a hybrid session with regards to we're going to spend about 5 minutes per team, so about 40 minutes, um, just discussing as a class your project proposals. And I'll try to keep us on schedule. And then I do want to just finish up the lighting topic and what that means in practice. That does intersect nicely with what Team One is going to be presenting here. So I'd like you to be the first and to start for us. So if you have one presenter per team is sufficient for this. I mean, ultimately, I don't really need every single person for any of your presentations to kind of share. It's nice if you're here to answer questions. But having said that, group one, whoever your appointed representative is, feel free to get started.
All right. So we were planning on having everybody, talk. So I mean, I guess if you just want one, I can
That's
talk
fine. That's
first.
fine as well, Matt. So let's just keep it timely. That's fine.
Okay. Yeah. So you want to move to our slide?
Yeah, I guess so.
Yeah. So our topic is that we wanted to implement deferred shading. I know this was something that was kind of suggested by Zambrino in the document, but more or less what deferred shading is the idea that you can significantly reduce the number of lighting calculations you're doing, right? So rather than doing lighting at a per fragment basis, where you're just calculating lighting for everything, for even objects that might be removed later on via depth testing or what on. The idea is that you can calculate these values at a per pixel basis, right? So you only can have as many fragments on the screen as you can have pixels. And this is done using, some additional math, normal vectors, and more or less determining where the surface is compared to, all the lights in the scene, and also the surface normal of, what direction is it facing relative to that light, and kind of what are some, properties of it. You can kind of see that picture there in the middle, where, you might have fragments that are not really shown, and that you'd have to calculate lighting for normally, which is, called forward rendering, which is kind of what we're doing right now with our MP4 implementation, whereas deferred only ensures that you're doing one lighting per pixel, right? And you can kind of see up on the right too, kind of the implementation of what we're doing. We only have one graphics pipeline occurring, where we've got vertex shader, they show a geometry shader and a fragment shader there. All this kind of pipeline just being put out to the render target, whereas, in real deferred shading, you're pulling all those values into some central point, and then you're doing that at once, right? Rather than actually doing the lighting in the fragment shader. So it makes it really efficient for high poly and high light count scenes, not to balloon your calculations you're doing. Braden, did you want me to take this one?
Oh, I could do it. I wasn't sure if you were presenting the whole thing. All right, so the general gist of deferred shading, like Matt just said, is to optimize for high light count scenes. So that picture on the top right, for instance, that scene is drawn with like 1,800 or so lights. So with that, insanely high number of lights, that would never be able to be rendered in a timely fashion using forward rendering. However, with deferred rendering, the actual number of calculations is significantly optimized because we only need to calculate it at the last stage, and pixels that are covered by other objects and would fail depth testing, those ones will never have to have lighting applied. So in general, our kind of target demo is going to be a little bit of a simpler one. That's going to be the sort of bottom set of images. We're going to take a simple scene with lighting on it and prove that we can defer the light rendering until the very end of our pipeline. And we hope that even with just this little toy example, we can have a sufficient performance increase that should actually be visible during a demo.
So I've asked the team this question, so I'd like you to expand upon a little bit of this. So this is showing it's multiple passes that are happening. Is that the deferring that's happening, where there's an initial pass that just pushes starting color, the next one that pushes light maps, and then they're kind of merged together in a final pass? Or is it multiple different shaders that are being loaded, or what is the mechanism by which we are going from this to this view of what's happening?
I think Matt will probably be the best to answer that.
Sure.
I have a better understanding for actually using GL light primitives, but
Yeah, so it can kind of be thought of as passes, but it doesn't necessarily need to be. So I think it's kind of small, it's hard to see, but the picture in the bottom left there, I think does the best. Generally how it's kind of represented like that is that, you've got a couple of things. You have your geometry going in, and then, like for instance, one of those pictures down in the bottom left that's stacked up, one of those represents, I think the second one represents actually the surface normals. One of them represents like the albedo. So that's going to be, kind of like your material. And so yes, those are kind of combined together. They can be kind of done in parallel though, right? Because for instance, you can calculate the surface normals the same time as, you're calculating the albedo and whatnot. And then, yeah, those are all those kind of, the G buffer, right, as it's referred to, right? The buffer that holds all the information for every single pixel on the screen, then, kind of gets taken from, that 4 buffer stack all the way down just to one image. And that's kind of where you get the output image there, right? And so you could think of it as passes, but I think it'd be better to think of it as, just additional parallel computations, right? You're computing a normal, you're computing the, the material, you're computing, the location based on the position, right? Where is the light coming from and whatnot as well too. And
So is it not rendered to texture? So do you not take this as input and then generate 4 textures that you then do a second pass and apply those to the scene?
Yeah, so that's one way that it's implemented. Yeah, is using textures like that. And so we're still kind of exploring whether that's going to be the best way for our implementation, or if we want to try to hardware accelerate that with like an additional IP core, or adding functionality to the render output beyond what our current texture implementation is going to be. But yeah, so that's one way in which it's done, is just creating multiple textures and applying them as well.
Okay, and just we're already going past my 5-minute goals, and that's not your fault. It may be possible that for your project, and I don't think for most teams that's the case, but it may be possible for your project that to implement this, you might wind up having to break some of the earlier assumptions we've made in our pipeline. And maybe the previous applications may not work anymore because it may be one or the other, versus this as being a special case of what we're already supporting. And that's okay if that's the case.
We're hoping to be able to add like a flag so we can go back and forth. We think that we should be able to do that right now, but yeah, it might possibly be once we dig into the details.
Cool. And our work breakdown is Matt's going to have a focus on the software shaders and OpenGL side. Nathan will be exploring the driver changes we need to make to support the G buffers and their allocation. Braden's going to be doing our general updates to make sure our hardware is up to date and all that. And I personally will be working on just top level design for adding deferred shading to our hardware.
Cool.
Not sure how in depth you want me to go due to time concerns.
Good point. And I didn't really think about it. Maybe just briefly just walk through what does 200 points look like for your team. I mean, people can read it as well, but you can briefly walk through it.
So with getting 200 points, that middle column there, kind of looking at getting that G buffer implemented and then creating the lighting pass shader. In addition to that, we want to have at least kind of planned out how we potentially would like to hardware accelerate things. And then have the software rendering implemented. And then in addition, we want to have an application to show off the deferred rendering if that is, using some of the previous provided examples and modifying them. And then potentially only having a single light source. And then for our demo, we want to be able to demo something using a deferred shading without hardware acceleration. And then we want to have a well-documented driver changes, hardware updates, and then the OpenGL application all documented well.
Thanks, Nathan. Thanks, team. And I think as opposed to just opening up mics for questions, if people have any questions or comments, feel free to add them into the text chat, and I'll speak up when there's any questions. I think you have some work to do. Every team has work to do. It'd be nice, of course, both to kind of demo applications we already have, as well as, and I think most teams will be in this situation where you'll want something that really shows, yes, this required our project. That doesn't mean it's overly complicated, but this demo, even if it's a very simple one, would not have worked with MP3 hardware or wouldn't have looked the same with MP3 hardware. So it doesn't mean it has to be more complicated, it just has to kind of take advantage of what you are doing, which is fine. It could be an adapted version of these or just your own application. As always, start simple, and then add complexity once simple stuff is working. I'm a broken record on that, I know. Team number 2.
All right. So our project is that we're planning on reconfiguring our current SGP pipeline to run on the Zinc UltraScale ZCU 106 board. As you can tell, it's a significantly larger board than the Nexus Video 7 that we currently are using. This board has more memory and a significantly larger amount of DSP and logic cells. So the goal is to hopefully allow future students of this class to work on projects without worrying about design size optimizations or size constraints. As seen from the above group, we can see that there's a potential of maybe even doing parallel pipelines. Our board simply cannot support that right now, and there's concerns as to how many cores, additional cores we can fit as we add more functionality.
Right, great point. And even if we don't worry about increasing capacity, it should be able to be just better for meeting timing of the current design. So less time spent in Vivado, more time doing design. That would be my hope for moving to this board. It's only 12 times the cost of our current board.
All right. So for demos, so yeah, to show that like we got it working, we're gonna hopefully be able to run most, if not all, of our previous OpenGL applications and show that they still work. And then also we'll show hopefully at the end that our utilization is not 3 or 2/3 of our chip. And this is pre-MP4, of course. So when we add MP4, we're going to be using even more of this chip. So hopefully it'll cut down significantly on the overall board utilization.
So we each are kind of taking a lead on a different part, but we are all going to be working on it together. Just each of us is in charge of making sure a separate thing gets done. Ryan's going to be working on porting memory systems, the subsystem, excuse me. I'm going to be working on porting video subsystem, and then Christian is lead on the Ethernet subsystem, and then Daniel is lead on porting debug and graphics subsystem. And we're all going to work on Git integration. We want to get a lot of the porting done in the first week or start early on with that. And then a lot of the graphics would be focused on the second week.
So this is our assessment rubric. So the bulk of our points are going to be coming from these subsystem attributes. And this was because generally, if we have our subsystems fully or successfully ported and they're completely functional, then generally our whole design should be functioning properly. So in order to get 200 points, we need to make sure that each of our subsystems are ported and functional. And then for Git integration, we want to make sure that all the necessary files are packaged into Tickle scripts and retrievable from Git. And then for our demo and report, we want to make sure to include all the key components and then analyze some of the board benefits. So thinking about what kind of performance improvements are there, maybe how much faster is route design, how much more capacity we have. So maybe thinking about how much more or how many more shaders we can include. And then in general, just what does device utilization look like?
So thanks, team. And something that I've mentioned to most teams, and I'll just mention one more time here today, is, for parts of the rubric that mention, complete report, well, part of this assessment is going to be your peer assessment. So we'll have our final demo day, and I'll be bringing up these slides again, or I'll put them in a Qualtrics or Google form type survey, and I'll be asking you just to give your relatively snap judgment on how you think the individual teams were doing. And it's okay. We tend to be pretty fair and honest with each other in an environment like this. So I wouldn't worry about your score with regards to that. But your goal is definitely to make it something that your peers can evaluate relatively quickly. For me, I can take a couple hours and read through your report and really determine, if it was a quality report. For others, when we get to this point, certainly assume your peers will have maybe a minute to evaluate every one of these, attributes. So certainly in terms of the demo, in terms of the presentation, and when you do give that final presentation, you should definitely bring this rubric back up and say, well, here's our own self-assessment. We fit right down the middle column, or maybe we zigzagged across, and overall we did pretty well. But I don't think people will have access to your Canvas submissions. Your peers will not have access to your Canvas submissions for this project at the time they're doing that assessment. And we probably wouldn't have the time to do that level of introspection into the other projects on a peer by peer basis. So straight and to the point, like this rubric is exactly the way you want it. So it can be assessed very quickly and I think fairly and equitably as well. So this all looks great. So thanks, team. Couple questions about Git integration. Probably, I'm guessing probably not just, well, it's up to you if you think there's better ways to do the Git integration, but just can you speak to what you meant by, and you mentioned it a few times, Git integration as a primary task for your team?
I think the goal right now is to just get it working with the current MP structure in Git. So just kind of being able to be slot in, just potentially having a different branch on the Git so that you can pull whether you're working on a Nexus board or a ultra scale board. We do have that extra flexibility with the exemplary if we find a more a better way to handle Git and the distribution of all of these files at a mass scale.
Excellent. Thanks, team. That was wonderful. Team 3, you are up.
Yeah, so for group 3, our project is to add support for our SGP hardware and to our drivers so we can run this basically bootleg Minecraft project on it that I found on YouTube and in GitHub. So any sort of, improvements to hardware and code as well. Realistically, I don't think we're going to get, more than,
well, it looks like you already have it working there.
Yeah. So, that's Nathan's really good at this stuff. So we're going to have an easy couple weeks, hopefully, because it's already going. Yeah. And then Saba, I think, is going to talk about the demo.
Sure. So basically just get the main features. We want texture mapping. We want, placing and breaking of blocks to work. We want some blending for the water. We also want, this perspective to look nice, blocks actually look square and, no triangles or anything. And then basically, if we can achieve this, then we might even add a couple new features like lighting sources or like a UI or, particle effects as you're breaking a block or something. But yeah, because this will possibly require us to refactor the person's source code a little bit to remove some API calls, that is, or just other general improvements for performance. Then the work breakdown, basically, me and Reed will be doing more of the software side. Nathan and Justin will be doing more of the hardware side, although to be honest, Nathan's probably going to be a big part of the process along the way. So that's basically what this slide is saying. Yeah, and then basically for the rubric, as I said, we're just trying to get, we're just trying to get Minecraft working. It's a very basic version of Minecraft, although if we should happen to get that working, faster than we think, we do have some ideas for, as I said, lighting sources, a user interface possibly, and then just general improvements, getting the frame rate up is something more exemplary we could do. Other stuff like with the hardware, not having to reprogram the board every time or whatever, but that's less Minecraft dependent. But yeah, I think that covers most of the points of this.
And I think Matt in the chat made a very good comment. And what is kind of a big unknown for all of us is, and maybe your team has done a little bit more of that, we haven't been doing a lot of stress testing of any of this, right? We've been doing basic function testing and saying, okay, and that happens at 3 a.m., the night before it's due, or a little bit afterwards, and then we're done. So it's not that clear for yours and for a couple of these projects that have some similarities in terms of your goals for it. What if it only handles 20 triangles? You're not gonna be able to make that much of a Minecraft clone. I think we'll be okay in the spirit of compromise with regards to that as well. But we really don't know that yet. When you have enough triangles in the scene as you show it there, that's going to be, if nothing else, a much more stiff stress test of our system and of your rasterizer than anything else we've done so far. It would have been nice if Teams got the Flex Seal application working, and you should try it again this week as you at least get depth working as well. And we will, we'll see. And that's okay. If it turns out that there's just some fundamental flaws in the way we're laying things out, or just tricky parts of our rasterizer that we haven't really explored yet, and things just lock up, we'll work around those issues. But there's a decent sized risk. Speaking back into senior design, that's a common thing you also see in senior design reports. Well, one of the risks is we may not actually understand our project all that well. That is true. It's not very meaningful. That's the case in all of these projects as well. But having said that, I think once you get that working, I'd be very happy to share the Minecraft story with the rest of the class. Group number 4, you are up.
So I made this game like a really long time ago called Super Hexagon, and as a group we decided we're gonna port this to the FPGA. And this game was originally written for like a calculator, and then I ported it to the 3DS, then to the PC, then to the Switch, then back to the calculator, now to an FPGA. So it's really just a playground of coding. So we plan on porting this game. And so that's a quick demo of what it looks like on the Nintendo Switch. And so we're hoping that we can get all of this working. So that includes the transparency of the shadows, that includes the text that displays on the top, and getting the fonts rendering. We're hoping to get this all working on the FPGA at a relatively playable TM kind of frame rate. So our roadmap, we're gonna start getting some of the MP4 stuff fixed because it's kind of janky right now. So we're hoping to get all of the MP4 stuff, some of the MP3 stuff that needs to be fixed still. We're gonna get that done, and then we need to restructure some of the code on the project to communicate with our infrastructure for the FPGA. We need to implement some of the GL draw elements and kind of just fix some of the OpenGL calls. And then we're gonna see if we can get a variable amount of vertices being drawn per frame. And if we can't do that, then we'll just try a fixed amount with zeroing the rest or something like that. And then, we're gonna get an A+ and it'll be summer then. So for the rubric, kind of the really great is it looks like what you see on the computer. So that would be transparent shadows. That would be, it renders the game in like, a full kind of screen way. Has, textures, text, everything working on the GPU. Not great means like we have at least something being drawn. We can explain why things are broken. We got it compiling with the new system, but maybe it doesn't, communicate well. And maybe textures, don't quite work, or we can, improvise something around getting the game to at least kind of show up, but maybe not really work. So that's kind of the scale there.
So thanks, Tim. And I think it's actually really cool, and it just happened this way by circumstance, that there's basically 3 teams that are taking on a similar project, which is, can I get a quote unquote real game? This one certainly qualifies, to work on this platform with what additional hardware and driver support we would need to get something much more real working. But what I think is pretty cool is it's all, you're coming from 3 different directions. And I have a hunch as to which approach is going to be less painful, but I don't actually know. So the previous team, Team 3, is porting, and I think they've done a good job of looking at the code and trying to see where the pain points would be. If they hadn't have done that work, I'd have been concerned for them, because porting really requires the code to be able to do that, and this is definitely a task of porting to a very restrictive platform. Then you have your team, who is also porting, but it's a code base that you've written and you've actually ported already multiple times. So you have, I think, at least you for the team, have very deep knowledge as to what this code needs to do. You can give a rubric based on functionality, and I feel pretty comfortable with you doing that, because you know exactly where that is in the code and what that requires for those different parts of the code. And then there's another team who's going to be making a game. I think effectively from scratch, and then doing the porting. And so 3 different approaches. I'll be curious to see, how well that goes. I think given your expertise and having ported to, I don't know, does the TI Inspire have better graphics than our SGP? Probably it does, right? So, but
I mean, I think it does software rendering, so
Okay,
I don't know.
well, yeah, depending on the library. So the Inspire, yes. So fine. I think given that experience, you're going to find that you know exactly what needs to be done. Of course, whether you can get it done is a different issue, but you know exactly what the path would have to be successful here. So I'm pretty excited about that, and I'm excited for all 3 teams and the different approaches and seeing how they come out. Group 5.
Cool. So we're group 5. We're going to be doing something called face culling, which is basically rendering out sides that aren't seen by the viewer. How we're going to do that, it's done using counterclockwise, clockwise notation, depending on where you're looking at. So taking this in mind, the triangle setup in our rasterization already calculates that. So based on whether it's a counterclockwise or clockwise, we can just tell it to not render that triangle. Yeah, next slide.
Yeah, so and then in addition to having the triangle face culling going, we are also going to implement a software shape library with the idea that it would be really nice to have a easy way to create both 2D and 3D shapes, kind of similar to if you're using a 3D modeling program and you can just create a shape. So the standardization of the shape generation would allow for easy face culling use, because it would ensure that as the triangles are written, they are wound in the same direction depending on if they're on the outside or inside. And an example call looks something like this, where you'd call for a generate cube. You'd specify the face corners, 4 corners for the front face, maybe the colors, the depth, and then which direction is the front. So whether the outside would be like counterclockwise or if the inside would be counterclockwise.
I think that'll be pretty cool if you get that working, just as a sort of separate contribution and a nice little app for us to have for our purposes.
So for the demo, we're going to have an application similar to what you see there, which is basically showing the back face of a cube. Our demo is going to be very similar. We're going to try to recreate it, but we're going to be able to enable which forward face or front face or back face is going to be shown. So we'll be able to toggle. And then along with the library, just basically showing that we can tell it to cube all the attributes, and then it prints the cube on the screen.
And then our breakdown of how we're splitting up work and some of our major milestones. Alexis is going to help with the VHDL hardware work and the OpenGL application for our demo and whatnot. I am going to focus on the OpenGL application and the driver changes that we need to make. And then Brian is going to focus also on the VHDL work and be our report expert, making sure we have a really good write-up. So like as Zambrino mentioned, the library might be useful in coming semesters. And Isaac is also going to work on the VHDL hardware and helping me out with driver changes. The milestones that we set up. So basic milestones. The first one for the software library is having a kind of documented way that we expect the library to interact with the program. So figuring out what the prototypes might be and what data gets passed in, and then actually implementing that as the second major milestone for the software library. And then on the hardware side, we have changes to the triangle traversal, triangle test, triangle setup, so that we know our functionality for the face culling is working as expected, and making the driver connections so that the calling registers are being set properly to match the OpenGL spec. And finally, having the face culling running on the SGP hardware.
And I'm still not convinced, which is okay, whether you actually need to touch these two, or if it's all just in setup. But that's the nice thing. You'll certainly find out as you get working on it, what parts actually need. We already detect the winding order of the triangles. And actually this picture is a good way of seeing it, right? We detect the winding order of the triangles relative to the post-vertex transformations. So we should already have that there. We just have to skip the triangle. But implementing that skipping the triangle appropriately will take some VHDL changes, and I think it'll be fun to see what you come up with for that.
Yep. And then here's our report. Satisfactory performance basically consists of, we have the face calling rendering out, probably with an application where you can like toggle between, do you want to see the outside of a shape or the inside? So kind of like in the one picture on the first slide where it had the cube and you saw inside, a similar 3D look like that. This demo would be using the library that we make to generate like the cube and maybe a few other shapes, basic shapes. And then we have some stretch goal shapes that are a little bit more complicated. And yeah, with the demo, we'd also have driver changes made so that the connections are working. And finally, we'd have a report that has all our major components and stuff documented, so anyone else could come and figure out what we did.
Very cool, team. And you know, same thing with regards to your report. When we give our final presentations, you know, we can trust you also that you have your report and you can do your own self-assessment of that. But then I think this will be the part that I think, based on what you can show and demo, you know, your peers will be able to evaluate. Group 6. Do I need to refresh this? Let's see. Is this roughly your slide? Looks like it's okay. All right, you're up, team.
All right, so what we're planning on doing is implementing anti-aliasing, and when we were researching it, there are all these different kinds of anti-aliasing. So we thought that probably the easiest super sampling or anti-aliasing to implement would be super sampling, which is just SSAA. And what that does in basic is it just like quadruples the resolution. So you're rendering twice the amount of pixels on each axis, and then it combines those 4 pixels together and then like averages out the color to display whatever the pixel should be at that point. So I think that'll give us a good basis of anti-aliasing, but it's obviously not the best performing. There's other ways like MSAA, which is multi-sampling anti-aliasing, that would probably be better, but for our purpose, super sampling was going to be okay. And then if possible, so that was 2 times. So 2 times is like twice the resolution on each axis, and then 4 times would be 4 times the resolution on each axis. So if we have time, we might try and implement that, but that might get very slow on our graphics card. I think hardware wise, we should have the resources for it though. And then we also want to.
Matt asked a question there that I think a lot of people are going to ask when looking at this. So is your plan to have a just higher resolution render buffer, but then convert to the 1080p, or are you actually going to then do higher resolution rendering and driver video output and things like that?
I think we're just gonna have higher resolution rendering and then just downsizing it in like render output or something.
Yeah, so render output may. I have to think a little bit about what that would mean. So you'd have a render. It's almost a deferred rendering, right? So you'd have a render output pass that does 4K resolution or something, and then a separate module that does like an intelligent copy to your actual frame buffer also in the render output. It's doable, but that's where a lot of your work would be sent. It's going to be very slow, but that's okay. This is already very slow. It'll just be slower.
To like make it faster would require using like these I don't know, like MSAA algorithms that only super sample like the parts of it that need to be super sampled, so like the edges of triangles and stuff. And I guess that could be doable, but just through working this semester, we'd want to we don't want to bite off more than we can chew.
But
'cause-
consider the alternate approach, and I know we've talked about this, so I'll let you continue. But the alternate approach, as opposed to trying to do a 4K output, which some of the clocking circuitry that may be a little bit of a headache, or even a 4K buffer, which we have the memory for. You could also just kind of take the opposite approach, which is now our 1080p buffer is the super sampled buffer, and you're actually getting
We were
configured
thinking
with-
about
to
doing
a
that as well.
640p or whatever output.
Yeah.
And that I know does work. So that's something you could dropping down. We know works, and the hooks are already there in the driver to do that. It should all work. It's the other way around that I think would be.
Yeah, so I guess if we wanted to implement the 4x SSAA, we'd probably want to render it at a lower resolution. That way we wouldn't I don't know, things wouldn't get too slow. So yeah, next slide. So these are our goals. Does someone else want to take that, or should I keep talking?
You're on a roll, Josh. Keep going. Oh no, Sam's available.
Oh, Sam.
I'm on my phone, so hopefully I don't sound like crap today. Auxiliary goals. We want to fix MP2 through 4. We want to get everything working. We want to get triangle fans and strips to work correctly. We want to have moving triangles, so MP3, and we want to fix all the flushing issues that we've had and that broke our MP3. For software testing, we want to make tests that display the anti-aliasing working, and then change the image, display it not working, and then just be able to go back and forth. The driver changes, we need to add functions that can tell the viewport and render output what the image, or that the image needs to be anti-aliased. We just have to add hooks in that say we want to do anti-aliasing or not. Yeah. And then some examples of anti-aliasing, and that bottom picture is kind of what we're going to be trying to do. So it just takes the 4 pixels and then we super sample, and then we go back down, or we downsize again to get the right. That's a really, I don't know why I chose that picture. It doesn't do much, but so you can see the line without anti-aliasing and stuff. Yeah, you can skip that. And then go back and talk about the rubric.
Yeah, so this is our rubric here. So I guess kind of similar stuff to what's on the goals. Just fixing the components. That's, I guess, our first order of business, because I feel like we're just building on broken hardware and it's just not going well. So I think for our final project, we'd like to build on something that actually works. And then we would probably start working on the super sampling and then the driver and the OpenGL test. We can divide that stuff up between the different people, but the super sampling and the anti-aliasing is probably the biggest part of our project. So we gave that the most amount of points. And then obviously the driver, we do need some driver software additions, such as the function that's able to turn on and off anti-aliasing. That way we can test if it's working or if it's not working. And then we also want to make an OpenGL test program and test scripts for both our super sampling and, or I guess we want to make our own test for the OpenGL to see if anti-aliasing will work. And then I think TCL scripts would also be handy in this situation. So we want to try and make those as well.
And we know it won't be something you'll be able to see on the camera. So you'll be wanting to use that utility to grab the frame buffers and blow them up and show, what the differences would be. I think that part's pretty important. I know I got a couple direct messages about, well, are they allowed to get points for fixing previous labs? I think absolutely. If you know that's how you're going to be spending a big part of your time between now, for this project. I mean, saying you're fixing your MP4 components is a bit pessimistic. You still have time to, do your MP4 assignment. But it's a necessary dependency of, we can't show this if we're not happy with how our rasterizer is working. Whether you need triangle strips and fans necessarily to work. So focus on the things that will directly impact your ability to show that this project is effective. I think that's fair game. If you're going to be spending 20% of your time roughly, kind of updating and correcting and debugging, then giving yourself points for that is,
I think that was our idea there. So
it's a bit cautious, I think. So that 2x SSAA, certainly if you have a 640p output, should just kind of sort of work with a just separate little render output pass, but that's okay. So you start from there, and then I think you give yourself some chances to do some fun things after you have the basics working, as with every one of these projects.
Mm-hmm.
Thanks, team. Group 7, you are up.
All right. So basically our goal is to create a game similar to the Bandersnatch game. I don't know how many of you played Bandersnatch on Netflix when it came out, but essentially it was this choose your own adventure where the creator went crazy. Now, we aren't planning to implement that, but the actual game that he was developing, Bandersnatch, it's essentially a 3D randomly generated maze crawler where you're going through it and you're fighting these monsters. Now, we chose this style of game because theoretically there's not too many triangles to generate, but it still can demonstrate all that we've been learning this semester from, 3D graphics, depth testing, and then one of our biggest focuses, implementing now clipping as well, which should speed up the processor without making too many compromises. So our final game is pretty similar to these images. On the left, you can see a basic boss that uses a texture implemented, yes, with a Dobby head. And on the right, you can see an example of how you can move through the maze. This was also chosen because it's theoretically not as much reliant on real time. And I think we've all seen that the performance is not the best on these boards. So playability with this shouldn't rely as much on having to make split-second decisions where the game really wouldn't be playable if it weren't getting 30 frames per second, 60 frames.
So what there is, though, if you notice, if you think this is a single quad or two triangles, is there's a lot of perspective, right? So that, well, and you could tweak if you decide that that's necessary, because you could always do some of the pre-transformations in software, but that perspective transformation we can do in our MP3 code, assuming it's working. But then the normalization afterwards, you need to get that division working, basically, and otherwise it'll look not as good as you would like it to. But that's something that we can have workarounds, and you can consider that part of just completion of MP3, where you're doing maybe division at the end of your MP3 vertex shader, because that kind of maze view has a lot of that deep perspective to it. So assuming that's just one rectangle here, you have to take that into account.
So as far as the work breakdown goes, Ethan is probably going to be doing software. Riley, you can see a depiction of him in the top right. I'm probably going to be doing VHDL, maybe the driver, depending on how many changes are needed, and OpenGL, probably in the later weeks if I did it all.
What does Team Potato mean? Is that a term, or are you just being silly?
I believe Riley was being silly.
Okay, fair enough.
Nolan's probably doing VHDL and diagramming. As far as major milestones go, by the first week, we'd hope to have the design planned out and diagrams finished. Second week, clipping implemented, level at least made, and textures are completed. By the third week, we'd hope to have movement and action, and by the fourth, finalizing.
Here's a rubric. It's not terribly clear, I guess. Resolution is not amazing, but for the demo, we hope to maybe have Zambrino pull up the live stream of our monitor and actually kind of show you guys the game actually performing.
And I recommend not doing that. I mean, I understand the desire to do that. Every time I've ever tried to do live demos, even in-person versions of this or other classes, they always just don't suddenly work. So record video if at all possible. For not, I mean, we could try, but it just never seems to work. It'll work 10 minutes before class, then you'll come to class and all of a sudden it won't work. So video is definitely the way to go, as we've been doing this semester.
Yeah, Nathan, maybe we will try that. For the hardware, we also had a portion of our final project that's kind of going to be catching up, cleaning the previous labs. And then clipping was the major hardware changes, and get those working, and hopefully the frame rate relatively performative on the FPGA. And then the software, the game working without bugs that are making it unplayable is kind of our satisfactory, with room to have all those bugs cleaned up in the exemplary column.
Thanks, team. I think it'll be fun. I mean, there's a little bit of a dependency, right? In that, you would want to have some semblance of the game ready to go to get a better feel for exactly what things, how much clipping is needed, and what other outstanding bugs from previous labs you actually have to fix, right? Ideally, you fix them all in practice. You pick the ones that you need to fix to be able to do this demo. So there's a little bit of that. So getting an initial skeleton working version of this that maybe isn't even a game yet. Maybe it's just a single frame of a scene that you'd want to be able to show that you can render. Getting to that point pretty quickly, I think, will help the team in knowing what your target is, and then you can make parallel progress on software and hardware. Well, thank you, team. Group number 8, last but not least.
Hey, so we're group number 8, and the main goal of our project is to optimize the performance of our shader cores by adding pipelining to like each of the stages. Bryce was the one who came up with this, and I don't think he's here right now, so I don't know too much about like the implementation that he was planning on, but we do know that we have to account for additional data hazards when we do this, and to know that our performance is better, we have to be able to measure the performance. So I plan on making a performance profiling software that will, given like certain various hooks in like our graphics pipeline, I want to be able to try to measure the time it takes for like a vertex to pass through like a certain stage in our pipeline, so that way we can try to figure out certain bottlenecks. And then also I want to make some OpenGL benchmark programs to try to see like what happened, or try to stress different parts of the shader core and potentially different parts of our pipeline in general.
So if I had thought about that before the start of the semester, I would have definitely included that. So if you look at how performance counters are implemented, modern hardware, there's hundreds of them now, and they're all individually very straightforward. So they're counters with enable start stop bits, basically, that you can then read via software. We have some of that infrastructure in place. A couple teams toyed around with that in previous labs, but just implementing that, I think, will be pretty valuable. I don't think it's anything more than triangle start, triangle finish. How long did it take? Shader program start to shader program done. Just a counter that just upcounts cycles and provides that as a register to be read from software, or anything else that you think would be important to be able to measure to understand the performance of this versus the performance of other parts of the system. Ideally, those would have maybe already been in place when we started the semester, but adding those now is also very doable. And I think, independent of how clever your pipeline is, because I think you're going to find the way our compiler is emitting code, there's going to be a lot of data dependencies. We're not trying to be too clever with the compiler. Either you have to mess with the compiler to make it more amenable to pipelining the code, or you're going to find your pipeline's not really any faster than not pipelining. I think that's very likely to be the case, but that's okay. It's still worth it as a project to explore that.
I should also add that we were also thinking about, or you can go to the next slide. I can talk about it here, but we were also thinking, or at least I was thinking, that maybe we could dynamically update the debug register, so that way, like, we could try to measure how much time we spend in a certain state in our shader core. But yeah, this is what we plan on demoing. I mean, because it's like a performance measurement, we mostly just plan on focusing on like the performance difference between our MP3 vertex shader and our optimized vertex shader. And because it's like this similar to the MP4 fragment shader. I mean, maybe we'll try to test that performance as well. Some metrics we'll try to look at are, we'll be primarily looking at CPI, cycles per instruction, but I kind of want to try measuring average frame time, like how long does it take to generate an entire frame, or how long does it take for like a vertex to just move through the whole pipeline. And we also have some OpenGL benchmark programs.
Okay, so
that I
that
was
part's
thinking
pretty
about.
important, right? Because when you talk about performance of a chip, it's not just running one. So having reasonable set of shader programs or OpenGL programs, I think that'd be pretty useful for getting a comparative view versus for this shader, it's 10% faster. Well, who cares? What is it for the workload that you've been able to generate? Benchmark design is pretty hard to do in a way that's fair and that stresses all the different parts of a system. I don't think you have to make a perfect benchmark, but a good faith attempt at a set of benchmarks, I think, would be a nice contribution for this project as well.
Yeah, I was looking at like 3 main like workloads. The first one was like a realistic workload, but now that I think about it more, I don't really know what that means. Maybe I'll try to generate something like the cube program in MP3. I forgot what that was called, but something like that. Maybe it moves so it hits. There's a lot of cache hits. A random workload instruction where there's not as many hits to the cache, and it's kind of just acts like just calling random instructions, and it'll stress like different parts of the what's like all of the operations in our ISA, and then a multi-cycle operation workload that really focuses on stressing like how fast is our like multi-cycle instruction implementations like fdiv, square root, fpow, stuff like that. And then for division of labor, Josh and Bryce will be mostly focusing on the hardware with VHDL, and I'll be the one like making a lot of the driver updates if any are needed, especially like with the hooks into the hardware. But also I'll be writing a lot of the performance profiling aspects in hardware and in software, because we might have to add actually not really, but I'm planning on maybe adding like ways to profile the performance of other components. And then some major milestones we'll be looking at are first like adding the hooks to the pipeline. Can our profiler measure cycles per instruction? How long does it take for a frame to go through? And first we want to get it functioning on hardware, and then we'll try to beat the performance of our MP3 shader core.
And I just want to add, I think, the performance profiler, building hooks to measure how many cache hits and misses we actually have, building counters that measure, average CPI for a given program. Those are all the kind of things that, modern microprocessors all provide for us. None of them individually are that hard, but taken as an entire effort across the different parts of this project, for this class project, that's very useful stuff. So, the pipelining, it's not that clear, how far you'll be able to take that, right? I mean, will you have enough insight to really be able to squeeze good performance out of a pipelined implementation? We have our MIPS ISA in 381 that was designed for pipelining, and even that, it's kind of a pain to get all the kind of edge cases working. Here we have an ISA which is designed such that Steve could call it done, after a couple of weekends of effort. And so it with that, perspective, it's probably not going to pipeline all that well. It doesn't mean you can't try, and it doesn't mean that you failed if it doesn't get great performance at all. But I think you're going to be fighting it a lot of the time that it wasn't made to be effectively pipelined. Every single compiler emitted instruction is going to have directive data dependencies with the one before it. You're going to be stalling every single instruction based on how this ISA was designed and based on what the compiler is generating. So, you didn't leave it as a task, but I think looking into the compiler would also be a valid direction in seeing how we can reorder things in such ways. And then also just the performance analysis part of this project, you know, would be really wonderful. There's also a question about, you know, out of order execution. Well, it could. I mean, certainly depending on how, and I think teams didn't get enough chance to really play around with the special function units in practice. But if we could have really high latency special function units, there are in theory all sorts of things we could do to allow for out of order execution. The compiler doesn't generate any code that's going to make your life any easier for that. So it is in theory doable. Anyway, it's the basis for a valid project. I also just think that even if you wind up building an unimpressive pipeline, and that's okay, but if you wind up doing that, this still can be a very successful project via you know, some of the other hooks that you're allowing here. And so possibly consider, and you know, if teams want to take tonight and do one more final revision of the rubric, that would be fine. If teams want to take one more time to review it, one thing your team could potentially do, because where I think there could be some fun, would be to give yourself just more points versus others. So pipeline is functional at 75 points. So really your pipeline's 125 points versus 25 points for debugging and profiling and benchmarking. Maybe if you kind of shift those around a little bit, I think it may more reflect where you'll be able to make where you'll be able to make progress for this.
Oh yeah, previously the like performance profiler and like the shader benchmarks, they were all like one big section of the rubric. And because I was in a hurry, I kind of just split them up and divided all the values by 2 almost. But yeah, the main 3-4 things we're looking at are how does our vertex shader like, or is it functioning? How well do we handle data hazards? Does our performance profiler measure cycles per instruction properly? And then do we have at least a couple benchmarks in which we can test the shader core and different aspects of it? That's all we really were planning on doing.
So I'm seeing some good questions about, you know, what are the actual challenges of data dependencies? I mean, we're also dealing here in your pipeline implementation with the realities of also meeting timing. So there's this extra level of partitioning of critical path and having your multipliers take multiple cycles. And, you know, the way we have it set up, there is going to be quite a bit of stalling associated with this because we can read right away. We could read in cycle 1 if we want to, or cycle 2. Even if we don't have any of those branches, the data dependencies are going to be involved just a lot of stalling. And so that's okay. So you can definitely build a pipeline, but do consider, because where I do think there's a lot of progress you can really make on there, do consider just bumping those up a little bit and bumping these down a little bit as well. But otherwise, I think all of these projects are great. You know, I don't know if we want to go to our continued lighting topic today. So I think we don't have to. You guys have any other questions about projects or timelines or anything with regards to for this course? In terms of our process, I'm going to lock this file, we'll say tonight at midnight, and just say locked it for editing. And that will be your final rubric. So if you need one more go at it, and none of them were wrong. So every single rubric as I saw it there, I had thoughts, suggestions, final suggestions, but they were all fine. So you do not have to change them anymore. I didn't open up Canvas for resubmission. So just consider these slides the final version. Make the actual table an actual table and not just a screenshot, so I can edit and copy it into other formats when you do that. But you don't need to resubmit on Canvas. So this will be our final submitted, a combination of what you already had in Canvas and what you have for this. And then when it comes time for your final presentations, I'll be asking you to kind of bring this back up, do your own self-assessment, and then at the end of each presentation, each of the individual other students in the class will be doing that peer assessment of how they felt you did. I have lots of final project ideas. Actually, to be honest, a little jealous of some of the projects you get to work on. All of those could have made good independent studies as well. I mean, to some extent or another, adding on to this, a couple of them could probably, lead to publication as well, depending on how much innovation you put into it. Because we know this is an academic architecture we're starting from. This is for teaching environment. It's never going to compete with anything commercial. It's not even going to come close to that. We know that that's the case. But as an exploratory tool, as an academic tool, I think there's still a lot of value to it there. So I'm a little bit jealous with regards to, you get to spend the next few weeks working on this, and I can only help out as needed. But let me help you if I can. Let me know where you're getting stuck. I'm gonna unofficially join every team, for the rest of the semester. I can only put in so many hours, but and Steve as well, be happy to do that and help where you're getting stuck. Certainly try to nudge you in the right directions for things. Oftentimes so far this semester, I felt I've been most able to contribute by forcing teams to kind of answer those why questions of, we know things aren't working. Screen is gray, screen is black. And answering those why questions helps to really nail down a proper bug report. And from there, usually the answer is something that we can figure out and we've been able to solve given enough time for it. So let's leave things here for today. I wanted to talk more about lighting, but we're kind of out of time, and it's going to kind of be, haphazard approach here. So we'll pick things up on Tuesday. Technically, Tuesday is what we have scheduled for our MP4 demo day. I'm looking forward to seeing your push for the rest of that MP4 assignment. I do think you should be able to get depth and alpha working. It's very doable. There's nothing that should be scary with regards to that. It's a little bit more driver work. It's a little bit more deciding as a team what needs to get done. And it's a little bit more open-ended, but you should be able to get that working for MP4 at least. So let's leave things here for today. And I look forward to seeing your activity over the weekend. And I'm looking forward for us to all move on to our projects. I think it'll be a little bit more fun knowing that you're in more control over your timeline and your success at the end of the semester. So thank you very much.